Jacob Heck is a geodesist serving as the National Geodetic Surveyors. Good Lord, surveys regional geodetic advisor for the Great Lakes. That is a mouthful. Where he supports users for the National Spatial Reference System throughout Michigan, Indiana, Illinois, Wisconsin, and everywhere else. As part of his position, he is active in the Vertical Control Water Levels Subcommittee of the Coordinating Committees on the Great Lakes, Basic Hydraulic and Hydrologic Data. Holy moly. Binational
Spit
group
it
that
out, Trent. Spit
maintains.
it out.
I know, good Lord. The
It's almost like a
binational
string of
group
made
that
up titles.
maintains, yeah, sorry, Jacob, that
Sorry.
maintains the International Great Lakes Datum. He has also worked for NGS since 2016 and previously as the GNS researcher for the Geoscience Research Division. Prior to that, he carried out GNS and gravity fieldwork throughout Bolivia, Chile, and Antarctica as a graduate research associate at Ohio State. Jacob has a BS in surveying engineering from Michigan Technological University, where he is currently serving as a professional advisory board, and a PhD in geodetic science from the Ohio State University, the Ohio State that unfortunately did not win this weekend. Sorry. He is also a licensed professional surveyor in Michigan. Jacob serves as the president of the National Society of Professional Surveyors Young Surveyors Network and a liaison between NSPS and the American Association of Geodetic Surveying, AAGS, and is active within the International Federation of Surveyors, FIG. And in 2020, he was profiled as one of the XYHT's 40 under 40. Lordy, sorry, I butchered the heck out of that, Jacob.
That's
We're
fine.
fortunate to have Jacob on again. He's been on in the past, but we were going to do this one a couple months ago, and time got away and got busy for him as well. So, and he was able to probably add a few more slides. I think kind of what we talked about. Things were changing over the last few months as well. So, time-dependent coordinates in the modernized NSRS. Jacob, I'll turn it over to you so I don't keep stuttering.
Thanks, Trent. And yeah, I will point out that since I graduated, all the Buckeyes are 1-4 in that game. So you can see
Oh.
what kind of an impact I had on the football team during those years. uh, so thanks for being here, everybody. I'm gonna talk about time-dependent coordinates in the modernized NSRS, and it kind of follows up on some of the things I was talking about last time when I was here, 8 months ago. Yeah, it seems like a lot's gone on since then. Um, so just what I'm trying to look at here is what things are going to look like as we move on to the modernized reference system. So not just trying to get away from some of the theory about it, get a little bit more into what it's going to look like in your day to day. But as you'll see, we still have quite a few unknowns there. But I think we have some broad lessons that we can learn from and think about and go through and get prepared because the modernized NSRS is going to be here soon, and we want to make sure that we're ready for it. And I'm trying to cut down on the number of phone calls I get after we switch over on that date. So I'll go ahead. I'm going to turn my camera off, and I'm going to this way I can have my notes up on my screen right here, a little bit easier. Um, so I'll start out with just some updates from NGS and announcements that we've had. NGS is still in this period of time in between permanent directors. So Juliana Blackwell retired back at the end of March. And since then, we had our deputy director, Brad Kearse, was acting as director for a while. Currently, Dr. Shahak Payeri, who is typically the division chief for the Geosciences Research Division, he's acting as director right now. And he's been doing that since about September. So we're still going through this period of change, and that may play into some of the timelines and some of the just some of the things going on. It's always difficult when you don't know who's going to be in the leadership chair um, in the in the longer term. So we're working through that right now. Um, but yeah, as I go, I'll give a little bit of a background on NSRS modernization. I think everybody in the room here is pretty well aware of what's going on, but just in case, I'll throw some of that in too. And then I'll talk about drifting coordinates and different types of coordinates and some of the things that NGS offers to help deal with the changing coordinates. So from a timeline perspective, it's almost like this domino effect of once one thing's done, then the next thing can kick off. We have a series of dependencies when it comes to what the final products are going to look like, what the final reference system is going to look like. So at this point, we have finished collecting the airborne gravity data for the whole country. So that was a really big part of the process that took about 16 years to complete. And then the next big step that we need to get done is this multi-year course solution 3 processing. So what that does is it aligns all of our cores in the network to the International Terrestrial Reference Frame of 2020. So this is a follow-on to the Repro 3 effort through the International GNSS Service, the IGS. So, and we're very nearly complete on that. Philip McFarland in October gave a webinar detailing our progress on that and what's left to do. We still have to look at some of the noise models, and we have to do some of the combinations still. But once that step is done, then all of these other pieces can then kind of fall into place after that. So we have a geoid model built. It's up on our alpha website, and I'll show you where that is fairly soon. But that's dependent upon this multi-year core solution 3. So the final version's not done yet. Once we have the core solution and the geoid model, then we can do our reference epoch coordinate adjustment to get the 2020.0 reference epoch coordinates on all of the passive control that we have in the database. And that's a really important step with this modernized system. From there, we can go on and develop the transformation grids comparing new versus old. And then we can circle back and finalize the state plane coordinates of 2022. And that's kind of going on in parallel. It's not all the way completed yet, but it's a lot of kind of like administrative work at this point because we have so many new zones, over 900 new zones across the country. We can't do them all at once, and we have to dedicate people resources in different areas, pull people off to work on other projects in the meantime. So that's where the state plane zones are right now. But once we have all of these pieces completed, then we have to go through a testing phase. And then it's not just NGS that can say this is the law of the land. It actually has to go up to the Federal Geodetic Control Subcommittee, which represents all of the federal agencies that use geodetic data. So once it goes there, then the FGCS votes to adopt it. And that's expected to come in early 2026. So that's what our timelines are looking like right now. And then I put this note out here, and this is something that Drew Smith has said in a couple of recent webinars since about 2022, when we realized we couldn't get all of our grand plans done on the timeline that we initially were aiming for. Work on additional tools will continue in the out years. So the reference frames will be completed, the geoid models will be completed, but we won't have all of everything going into Opus the way that we wanted to when we began this process. But that will come as the years go on. However, in the meantime, we are working with our industry partners to make sure that we're using file formats that are consistent with what they can use. So that way they can build the modernized National Spatial Reference System into their products, into their tools. So we are working together on this, and we've had a couple of industry summits in recent years where we've brought in some of the key equipment manufacturers and software developers to get their input and to see what their needs are. So it's a big community effort. We recently put out a Federal Register notice that outlines the timelines that I just mentioned. And the wording on it's kind of vague. We will roll out components of the NSRS over time, so between 2024 and 2026, and it shows where that will go. And once it's up and made public, then it's available for public testing. NGS can take that feedback and incorporate it in there into these products. The testing will continue for at least 6 months after the final component is released on the beta website. And then, barring any unforeseen issues, in 2026, we expect the current National Spatial Reference System to be replaced with the modernized one within a few months of Federal Geodetic Control Subcommittee approval. So in that, when the FGCS meets and votes to approve it, then they put out a Federal Register notice, and that gives a countdown clock as far as when this will be adopted formally. So you won't find out the next day that, oh, this is what we have to do now. There will be some additional communication that goes on. But if you want more information about that, I recommend watching Drew Smith's webinar from February of this past year. He gets into the timelines and what all these components are and why it has to be rolled out in the manner that it is. But in the short term, though, we continue to update some of the tools that we do have online and make our information easier to access. So we have these 4 new tools that recently came out that I wanted to point out. DS World Web passive, which enables you to submit updated information on survey marks that are available on the data sheets. And then the passive marks pages, those are an expanded version of the data sheet, where instead of black text on white background, it has photos, it has information about what survey projects these marks are a part of, and other information like that. And then the leveling project page plays in with that as well, where it brings out the information that we really didn't have online before, but it will show you all of the marks that were included in a leveling line, in a leveling campaign. And then the calibration baseline web map shows where the latest calibration baseline information is. So it's an easy map to scroll in, scroll out, and find calibration baselines near you. You can. I'm not going to go into what all of those are right now. They are available on the NGS website, and I will point out where the NGS map is. So from this NGS map that I have a link to up here, and it's actually not in beta anymore. This is an old screen grab. This is the current web link, though, for it. If you zoom in on a mark, click on it, you can bring up the information where you either get the data sheet or you get the passive mark page. And if it's a leveled mark, then you can get the leveling information on it from the leveling adjustments. So it's handy. I use it quite a bit for work and when I'm on vacation and wandering around looking for benchmarks. So in addition to that, we have our new cores pages available now. And those are accessed through the cores map, which is that link down at the bottom there. So if you bring that up, this is the information page that you're taken to now. So it has all the information from the previous cores information pages, but it also has a lot more information on there, including cycle slips and other quality indicators like that. So yeah, go ahead and take a look at some of those. And yeah, access it directly from the CORS map. And the link that I have up at the top is what the link is for this particular page, this Big Rapids, Michigan station. So go ahead and take a look at that. Our beta web page, this is where we have public-facing testing for NGS products and services. The only thing that we have up right now is multi-GNSS Opus, our Opus Static 5.0. So if you're doing any Opus processing, go ahead, try it out, and tell us what you like, tell us what you don't like. Yeah, I want to point out this ngs.feedback@noaa.gov. That's a great way to get information back to us for how we can improve things. And that's for any product and service that we have out there. So today I'm going to get into what we outlined in our blueprint documents. So the first versions of these came out in 2017 and 2019. And then we revised them in 2021 after we you go through a few years, you learn a lot more about what this thing is going to actually look like. So blueprint part 1, that is covered in the that covers geometric coordinates, terrestrial reference frames. So replacing NAD 83 and other frames like that. Blueprint part 2, that's geopotential coordinates and the geopotential datum. So anything having to do with gravity, with water flow, replacing NAVD88 and other vertical datums like that, and the other pieces that go in there, the gravity field and those kinds of things. And then blueprint 3, that's working in the modernized NSRS. So that gives you an idea of how to take the information from one, how to take blueprint part 2 and make it applicable to the work that you do. And these are in the publication library, and I see Trent's given the links as I go. So thanks for doing that. So blueprint part 3, at the end of that document, we have 3 use case scenarios that we walk through about what that's going to look like, where if you're working on time-dependent control in a flood mapping project, or if you're using passive control for a multi-year corridor project, transitioning large data sets to the modernized NSRS, and then infrastructure monitoring. And we use an airport survey example. So we look at the work that's being done today in the current horizontal datum and vertical datums that we have, and we imagine what that's going to look like once the time-dependent reference frames come out and the time-dependent geopotential datum comes out. So it's intended to get you thinking about, well, what types of information do I need to be holding on to, what the metadata needs to look like, and how to plan a project over certain time horizons, where we're moving away from assuming that mark in the ground is always going to be the same the way that we've treated it in the past. Now we're embracing that time-dependent component. So taking a step back, the first thing that what modernization is, it's replacing the existing datums that we have at NGS within the National Spatial Reference System. So currently we have NAD 83 2011, NAD 83 PA 11, which is for the Pacific Plate, NAD 83 MA 11 for the Mariana Plate. And those are the horizontal datums that will be replaced with these terrestrial reference frames that connect directly with the International Terrestrial Reference Frame. So they're designed to be global and tied to the center of the Earth, and to work directly with the height system. And then we're also replacing NAVD88 and all of the other vertical datums that are out there in the different areas that you can't level to from the mainland US. And then that will be one consistent geopotential datum, NAPGD 2022. And that will work interoperably with the geometric reference frames as well. So they're designed to work together. Whereas in the past, the leveling crew would walk right past that triangulation mark and set a new mark for the leveling campaign right next to it. So shift happens, and we'll see that coming up here. So go from NAD83 to NetRef 2022 for most of the viewing area here. And that's what it's going to look like right here. So if you're out there measuring and you seem like you're off by about 3 feet or 4 feet or 5 feet, then you may be, one of the first things to check is, am I using the correct reference frame? Am I still using NAD83 or do I need to be using NetRef 2022? So that's how big the shift is, the direction of the shift. But I think the big thing to keep in mind is you're not trying to merge in your old coordinates. You'll need to get everything into a common system as you're doing your work, and make sure that it's in a common system. And then from NAD83 to NAPGD 2022, this is about what that shift is going to look like. So that there's a general gradient from one side of the country to the other. The NAVD88 has a tilt built into it. So by the time you're up in Washington State, it's off from the rest of the datum by a couple feet. But you can also see these little pockets as you go from one side of the country to the other, where you'll go through one color and then you'll have pockets of another color. And I think some of what's helping that is the consistent gravity data set that we have. But this is one of those areas where the GPS on benchmarks campaign, I think, was really going to help us when it comes to the transformation tools, because it's not a smooth, consistent grid going from one side to the other like we had with NatRef 2022. So looking at it on the height side, because there are so many other factors that play in, where it is a more complicated approach. And when I say these work together, they're interoperable. Well, here's kind of the story that I've been trying to tell about it. So we have the Earth. So if we started out as kind of a flattened sphere, an ellipsoid, that's the first approximation of what the shape of the Earth looks like. And then if we put the geoid model on top of that, so the difference between the ellipsoid and the geoid, that's your geoid height. So that gives you a connection between the geometric frame and the geometric frame and the geopotential frame. And in the new system that we're putting out, they're defined to work together. So they both connect at the center of the Earth. The primary axis for your physical heights, for your geopotential datum, for your height system, your which way water is going to flow, those are first realized through the geometric coordinates. So you get your ellipsoidal height from GNSS and then apply the geoid model, because these are defined to work together. They're both geocentric, unlike NAD83, which is not geocentric. It's offset by a couple meters from the center of the Earth. And unlike NAVD88, which is tied to water level stations, or a water level station around within North America, and then leveled from there. So it really doesn't have any connection to the center of the Earth. But now with these new frames, because they're developed from satellite orbits, from GPS, from decades of GPS data, as well as satellite information about gravity. The GRACE mission is one of those foundations, and that orbits about the center of the Earth. So these really do connect now in a way that the old systems did not. So if you've used the old hybrid geoid models like geoid 18 or geoid 12, those had to be rubber sheeted a little bit to get them to work, because you're trying to realize NAV88 heights from an NAD83 ellipsoidal height, and you have a couple pieces that don't quite fit together there. But with the new system, it should be a lot more streamlined. It's designed to be a lot more consistent. So we access our heights through the geometric frame. So if we work up on the topography, and then we have the geoid beneath that, and we refer to an ellipsoid, what that looks like is we go out and measure with GNSS, we get our little h. And if we want to get our orthometric height, the big H, that's the physical height that tells us more information about which way water is going to flow. And the difference between those is found in the geoid undulation. So that comes from the geoid model. So if you're out measuring in NatRef 2022 and you get your little h from your GNSS, and then if you apply your geoid undulation from the geoid model that's provided from NGS through geoid 2022, then you can get your NapGD 2022 ellipse or orthometric height. So it's streamlined. It's designed to work together. So let's start looking at the geometric reference frame. So if we start with our worldwide ITRF solution, realize our positions in a global frame, first thing that we have to do is take out the dominant plate tectonic motion. So, and that's characterized as a rotation about what we call the Euler pull. So that's named after Euler from Euler's theorem. And he said that all motion on the surface of a sphere is shown by a rotation about a point on that sphere, on the surface of that sphere. So we take our ITRF coordinates, we look at what that rotation looks like, what that overall plate motion looks like at all these stations, and then we solve for which way it's rotating and about which point it's rotating. So that's how we figure out the Euler pull parameters. In addition to that, we have our intraframe deformation model, which shows what the residual motion is. So if you're looking at the positions on the surface of the Earth, part of it is from the plate rotation, but there are other pieces that go into it as well. So what's left over is shown in the intraframe deformation model, the IFDM. And all of these reference frames will be solved in a similar way. And here's what it looks like if we're on the surface of the continent here. So if we have that point out in Indiana, you can give those coordinates in ITRF, or you can give those coordinates in NatRef 2022. However, as time goes on, those ITRF coordinates are going to change, whereas those NatRef 2022 coordinates will stay about the same. So you can use either frame or any of the frames. You could use the Pacific frame, or it'll just change more. But that's what it looks like, and why it's important to know what frame you're using and the time epoch that you're using. So a lot of these pieces that I mentioned, as they're ready, they first go onto the alpha site that NGS has. So you can go and explore that if you'd like, where we have preliminary values for the Euler pole parameters. We have a preliminary version of NCAT, the coordinate conversion and transformation tool, which gives you the ability to start working with the state plane coordinate system of 2022 to at least compare using ITRF reference coordinates there. And we also have the alpha version of geoid 2022. So, and we just had an update come out for that a couple weeks ago. So that is moving along. So, but anyway, anything up on the alpha site is preliminary. So we could change it. We take it down, change it as needed if something's not working out. So it's had some internal testing, but it hasn't gone through all of the vetting checks that we have for what's up on the final website. So, but this was something that that some of the industry partners were asking for, so we could make things available, so they could start putting placeholders into their software, and so they could more easily switch over once the final version is ready. So, why do coordinates drift? Well, so if we look at ITRF 2020, these are the velocities that we get for CONUS. But if we take out the plate rotation, this is what the NatRef 2022 velocities would look like. And in California, we still have quite a bit of motion out there because of it being on the Pacific plate, but also in the Northwest region, you do get kind of that rotation coming back in from that subduction zone there. But even across the stable part of the continent, you still get these different motions in a little bit different directions. And these come from a few different things. So over the northern part of the continent, we have glacial isostatic adjustment. So, and that impacts things mostly in the vertical, but also in the horizontal a little bit too. So when the ice sheets were sitting over the top of the Hudson Bay region, they pushed the mantle material underneath that part of the continent off to the sides. So all of the weight from the ice pushes down on the crust, which pushes down on the mantle underneath, and it pushes the mantle material out to the sides. So then when the ice melted about 10,000 years ago, we still have this ongoing rebound effect where the mantle material that had been pushed out to the sides is moving back to its original location there. So what that's doing, it's kind of like you're pulling up on a bed sheet right at the middle of the Hudson Bay. So in the vertical, you get this really strong vertical uplift right about where the middle of the ice sheet was. But then where the mantle material had been pushed out, that had pushed the land up, and now that's going down. So if you go across the Great Lakes Basin, for example, you have about 3 or 4 millimeters of subsidence around the Chicago area. But if you get up to the other side of Lake Superior, you have about 3 or 4 millimeters of uplift due to GIA per year. So that starts adding up over the years. And then in the horizontal, also you get this kind of a velocity field where, think about pulling the bed sheet up. You have, so where it's going up in the middle, everything around it's kind of coming towards it in a horizontal sense. So that's one cause of motion. And then we have some other areas of subsidence that you may be more familiar with. Water with fluid withdrawal, whether it's water or oil or things like that. So as you take that out from the basin. It causes compaction, causes the ground to go down. But even in a larger sense, if you have that the water leaving the area, so you may get subsidence locally, but in a broader regional sense, you may actually be getting uplift as well. And I think we've seen these big examples of 8.5 meters over 50 years of the ground going down in some of these places. So that's in the vertical. And then we also get episodic motion from earthquakes, which can be in the vertical and can be in the horizontal as well. And that can come in different magnitudes and in different directions. So that it's a little bit more complicated, but especially in areas near plate boundaries, you're more susceptible to an earthquake, and that can drastically change the position in a very short amount of time, but there can also be a longer term transient effect with it too. And then seasonally, we can get seasonal signals in the horizontal, but especially in the vertical. And continuous GNSS stations have shown this for years. And I show this example from this is a station in the Amazon basin. And the Amazon has a very strong wet season where the rains come and they'll fall up in the mountains, and then that water will flow downstream. And as it flows downstream, you can kind of watch all the stations along the way kind of get pushed down at a different time. And then in the dry season, where you go months without rain or without much rain, things dry out. So you get this uplift effect. You don't have the weight of the water sitting on top of the ground, pushing it down, but it gives it a chance to come back up. And over longer periods of time, you can see where there are years of drought, where at the bottom of the trough, it doesn't get pushed down as much because there's not as much weight of water there. And then during a wet year, you have that extra rainfall, it's extra mass, so that pushes the ground down extra far. So this is so common that ITRF 2020 is incorporating these kinds of nonlinear terms in their station trajectories. So instead of just having station position and velocity, they have a seasonal term component to them as well. And we're evaluating doing that at NGS right now. And part of that is because we're designing our system to match the ITRF. So if ITRF is doing it, then we should probably be doing it too. But I think the course team is actually doing it in kind of two different tracks, where you can include the seasonal oscillation, which is just an up and down in addition to the velocity. So if you leave it out, then your errors will get bigger, but overall, your long-term trends should stay about the same. So, but we should have some new guidance coming out on that once this multi-year course solution 3 is completed. And then regionally, we can get some coordinate drift as well. I first gave this presentation at Illinois. That's why I focus on Illinois here. But this is after taking out the Euler pole rotation, this is where what the trend still looks like. And you can see these arrows, they kind of follow that. They're going towards the Hudson Bay for the most part. And you get a little bit of rotation in different places, and they're moving a little bit different direction. But you can see there is some leftover motion after you take out the Euler pole. And you see that in the uplift too, or some different areas of the uplift over in the other figure. So I talked about changing latitude and longitude and changing height. We're also looking at the changes in the geoid. So if you remember, your height had to do with your ellipsoid height that you get from GNSS, your geoid height that you get from the geoid model. We're going through and evaluating changes in gravity and deflection of the vertical across the country to see if we need to include a, a dynamic geoid. So, we are putting out a dynamic geoid product showing change in the geoid in millimeters per year or fractions of a millimeter per year. But we've deployed absolute gravity measurements across much of the country where we're going back and revisiting those every 5 years or so to see what the change is. And then we had we called it a mini GSVS, the Geoid Slope Validation Survey that we'd done in other parts of the country. We sent teams up there with gravity meters and deflection of the vertical and GNSS equipment to revisit old benchmarks that had last been observed shortly after the 1964 Alaska earthquake. So we were looking at the differences there in these transects across parts of Alaska, because that's the area that has the biggest signal when it comes to difference in the geoid. That's because you have this big subduction zone that has potential for great earthquakes like that 1964 earthquake. So that moves a lot of mass, and which leads to mountain building. You have some really high mountains in that area, but there's also mountain glaciers up there. And as those mountain glaciers change in size, then the geoid signal also changes in that area. So it has the right mix of different things. So that's why we went there to do those measurements. And I haven't seen the results from those yet, how much things have changed since 1964. They were just up there a couple of years ago, and they'll be revisiting every so often to evaluate that. Yeah. So I'm going to step back and give a little bit of a refresher on active control, passive control. So the old datums were built off of passive control. We had marks in the ground, we had measurements over 100 years, and we averaged those out to come up with the best that we could do. But in the recent era, we've had continuous GPS running. So a CORS is an example of active control, and this is what we're using for frame definition and primarily for frame access. That's as opposed to passive control, where with the old reference frames with NAD83 and NAVD88, you bring up a data sheet, go find the benchmark, and start measuring, and hope that nothing changed, hope that a snowplow didn't hit it, hope that everything's in the same place. So with the direction that we're headed, it should make things easier to keep up with, more consistent. And following up on this passive control, so we've got two kinds of coordinates that we're really focusing on. So we have reference epoch coordinates, which if you look at the positions of everything across the country, and you take a snapshot of it every 5 years. So reference epoch coordinates will be referred to epoch 2020.0, epoch 2030.0. So these are regular time intervals, very similar to NAD83 2011, epoch 2010. So we're looking at publishing those every 5 years or 10 years. And it gives you something that it's something that we're familiar with. It's something that we're comfortable with. And it's something that it doesn't matter what day the data were collected. As long as you have all the information associated with it, it can go into these adjustments and get moved through time to that common epoch to tie in with where everything else was in the country at that time. Now, we're also providing support for survey epoch coordinates, what we're calling survey epoch coordinates here. So this really brings out the time dependency. So the coordinates that you get are from the day that you're out there observing. So these get thrown into shorter term adjustments where there's still a need for redundancy. There's still a need for checking your work. But you don't have to wait years and years for that processing run to go to update everything across the country. So it gives you flexibility to use what you need to use for the project that you're working on. And then here's a graph of what that kind of looks like. This came out of the Blueprint Part 3. So if we go out and observe on this mark at the purple times, so we have our observation and we have our error bar. So these are the survey epoch coordinates on this mark. The same mark, you can see what it's doing over time. And you can see what it's doing at that date that you measured. Now, when we get into the reference epoch era, so if NGS runs a nationwide adjustment for 2020.0 and 2025.0 and 2030.0, well, this information from the survey epoch surveys, I'll call it, it's kind of redundant, but from the surveys themselves at those epochs, those get thrown into the adjustment and move through time to these common epochs. And what that does is it gives you coordinates at 2020.0 where you can compare that with another survey that was done some other year in some other area nearby or far away. But it gives you something to compare against. But it also makes these error bars larger. So that's the trade-off, where the survey epoch coordinates are right at the moment that you were taking that observation. But the reference epoch coordinates, they have their utility, but you get a bigger error bar with it. So if we're working on a big road project that's designed to be built over 10 years, what do we do? How do we do it? So the contract says that the project must be tied to the NSRS. So we'll start out using an RTN aligned with the NSRS at Epoch 2020. But after a certain amount of time, eventually that real-time network's not going to be broadcasting 2020.0 coordinates. It'll change its reference epoch, and then you'll have to work with what you have then. So, yeah, in this case, though, you might want to use the 2020 reference epoch for the entire duration of the project, because that's what you started with, that's what you know, that's what you're using. But if you're doing that, though, you will want to set up some kind of rules for how much drift you can tolerate to see how much of a change there is from 2020.0 to, say, 2030.0. So some of that may depend on where you're at, what part of the country, what is susceptible to motion. And I think another thing to keep in mind, and this is the same thing that we would have to deal with now, is what if an earthquake happens in the middle? How do you recover from that? How do you go out and resurvey? How do you revisit, recover your control? So the way that we outlined to do it in our example is recover the existing passive control that you have around the project, establish your primary and secondary project control, and then you're working off of project control. So you do things locally and then tie it in with the larger network. Use the real-time network to occupy and assess existing control and observe on the added control. And then run your differential leveling between control to derive the orthometric heights. And then compute and publish project control reference to the selected reference epoch, matching the RTN broadcast epoch. So again, do things locally and then bring them into the overall frame at the selected reference epoch. And then from your control, everything ties in there. So you're connecting your static GNSS, your RTK, your RTN, conventional total station, differential leveling, and all of the other cool toys you get to take out there and use. So laser scanning, LiDAR, photogrammetry. It doesn't matter what instrument you're using to make the measurements. What matters is how good are those measurements, and how are the errors quantified, and how does everything connect together. And control is what we've always used to do that. So tying it back to those coordinate types. So as you run your control survey, so running through static GNSS, you can process and get your survey epoch coordinates. And from there, you eventually get your reference epoch coordinates, move it through time using the tools that NGS has available. You can run your real-time network survey to get reference epoch coordinates, so tied to what reference epoch is being broadcast from that network. And then with your leveling survey, you can get your survey epoch coordinates or your reference epoch coordinates, so tying in with the other control that's out there and moving it through time as appropriate. So, but one of the important thing is to monitor the project control over time, doing your test calibrations. And it's just like how I was taught to survey early on. Always go out, check in with your control, and make sure things are lining up. Make sure things are doing what you expect them to be doing. And if they're not doing that, then you have to go out and figure out why, figure out what's going on. And one of the big things to really think about as you're doing it, where we understand what's going on, we know what to pay attention to, what to work for, how to be thorough, but not everybody else does. And as surveyors, we go out and we're the first ones on the site, we're the last ones on the site. But in between, think about how many other people come out there and use that same information. And what do they use? They look at it and say, these are my coordinates, I'm going to pick up and run with it. But as we work with CAD managers and design engineers, construction inspectors, anybody using machine control, and then where these data sets go downstream, some of that information may get lost along the way. Assumptions may be made, and somebody may use this data in a way that it wasn't intended. So that's why it's important to have your metadata very clear. What reference frame you're using, what reference epoch you're using. Are you using survey epoch coordinates or reference epoch coordinates? And to make sure that everybody's on the same page that way, and that the data that you collect and pass along doesn't get used in ways that it's not intended to. So at NGS, and I touched on a couple of these things earlier. So you have NatRef 2022, you get your NatRef 2022 coordinates, but you'll get them at one epoch, and if you need to move them to another epoch, how do you do it? Well, that's where this deformation model comes in, the IFDM 2022. So that enables you to move these coordinates through time. And we also have the dynamic geoid model, which accounts for changes in the geoid between these epochs. So those will be built in to NGS tools such as Opus and Opus projects. It's like today where HTTP is built into these programs to move them through, to move coordinates through time to get the adjustment done at a common epoch. Um, so the workflow is really not changing that much. There's a lot that NGS is providing behind the scenes that you don't have to be an expert in deformation models. You just have to know what you're using and how and what how you're getting from point A to point B, what's in between there. Then in addition to that, NGS is providing and updating the coordinate conversion and transformation tool, NCAT. So that lets you move between datums, move between coordinate types like latitude, longitude, and height, and geocentric XYZ. We also provide data delivery, either through data sheets or the improved mark recovery tool, the improved mark data delivery that we have. So those are getting an update to get the full spectrum of information that's actually there. And then the other thing to pay attention to is the uncertainty in the tools. So if you think about on the older data sheets, we would publish coordinates to 1 decimal point or 2 decimal points, and that gave you a general idea of your accuracy. With the new system and the newer tools that we have available, like the newer geoid models, we have the error grids associated with them, so you can see what your coordinate is and then what the plus minus on it is, and that tells you a lot more about the uncertainty than publishing to fewer decimal points. And then coming back to the metadata, what kind of information you include on there, and make sure that your project plans include and any data that comes in, that it's treated the right way. And I took some of this messaging from Dick Kleinman up in Wisconsin. He's the NSPS director from there. We had done a joint presentation when he was still working at Ayers, so he had the perspective of somebody running a really large company, private firm, who got to watch where their data went. So that really kind of rang home for me what the metadata meant and why it's important, and the culture aspect of it, where making sure that it is considered a crucial component of documentation, not just here it is, go and run with it, but the why, the understanding and thinking about where things were coming from. So you can look at horizontal datum and epoch and vertical datum and units and just how things were derived. So if you have to go back and retrace your steps, you can do that in a meaningful way. And then here's some examples. Here's an example that we have out of the blueprint part 3, where we're looking at which terrestrial reference frame we're using to get latitude, longitude, and ellipsoidal heights, what the orthometric heights are in, the datum that they're in, which reference epoch we're using, what unit we're using, and then the projected coordinates, what system those are in. And then including a note on there about how the orthometric heights were determined. And if they were done by GNSS in a geoid model, that's just having that information that it was GNSS with a geoid model and combined leveling with it. So, and then the most accurate way to change your data between different reference frames, different realizations, best way to do it is to resurvey, but that's also the most expensive way to do it. The next level is readjust, take your existing observations and then readjust them into the new system. And then down at the bottom, the least accurate but the easiest way to do it is through transformation. So if you get through a model like NADCON or VertCon, these are built into NCAT, which depending on what you're trying to do, depending on how you collected your data, depending on what you want to use it for, and your accuracy needs, any one of these could be a real option. And then I want to mention the NCAT tool once again. It converts between coordinate types. It transforms between datums. It brings in NADCON and VertCon. And with the modernized NSRS, it will also work with the terrestrial reference frames with the geopotential datum. But one note is this is considered a mapping grade transformation. So every time you go through, you have the error in collecting the observations, you have the error in the adjustment, but you also have the error in the transformation grids. So, go ahead, use it. It's a great tool, but just pay attention to what you're using it for and make sure it is the right thing to do. So as I wrap up here, we're going through a lot of changes. The world has changed a lot too, with GPS being available, with years of satellite observations, being able to get these gravity grids and all the other information that we didn't have back in the 80s when NAD 83 came out and NAVD 88 came out. But some things don't change. Good surveying practice doesn't change. Purpose of the NSRS doesn't change. It's the foundation of nationwide geodetic control. And then NGS relying on your submissions for the upkeep of coordinates, that doesn't change. When blue booking came about in the early 1980s, that was a pretty big game changer. Now that I think about it, because prior to that, everything that NGS had in its archives that was collected by NGS. So we knew where it came from, who did it, and what to expect with it. So by coming up with the Blue Book process, that opened it up for people outside of NGS to collect data to a standard that we could trust and check and appreciate and use. And that opened up our capacity to take in more data than what we could before. And that process will stay the same with the modernized NSRS. The procedure will be a little bit different, but overall, we rely on outside some middles to us to keep up the data. And then working in the modernized NSRS will more accurately account for the true dynamic nature of the Earth's surface, but it requires a robust strategy and detailed metadata to ensure a successful project. So we can do so much more, but we also need so much more. And we have some more links here, and I do encourage you to sign up for the newsletters to stay up on what NGS is doing. And you can reach out to your geodetic advisors, and but we have quite a few quite a bit of interesting content on our website. So anyway, I'll open it up for questions now.
Got to unmute my other one. As you present all of this information every time, all I can think about, and just in my 29 years, I started with a 48 data collector and 5,000 coordinates, and then you just start to think about all of the changes in my 29 years and what another 25 years and what these changes are going to be. So it's blows my mind every time, but it's It's so in depth. So I love it. I was thinking the same thing with George. He kind of sent me a private one, but I was thinking of George, 50 years, 55 years of surveying, right? How much change you've seen. So it's pretty wild.
But you know what? So after, I want to tie this back to Joe's presentation from a couple weeks ago because
Yeah.
his was the most recent, right?
Yeah.
So,
Yep.
since then, I've been thinking about the PLSS a lot more. I actually gave a historical presentation recently about some of what Joe was talking about, but I got digging into there's a good book about Blaze's posts and stones about the PLSS in Ohio, the test bed for it, and it gets pretty well into the history about the land ordinance of 1785. And I know that's it's not a geodetic survey, but I think a lot of those same concepts show up, and I think we have a lot of parallels there. Where if you think about it that way, if you're out in the seven ranges, you have a reference system. You know what reference meridian or what principal meridian you're using. You know how many townships over, how many ranges over you are, and you know what section you're in and what fraction of the section you're in. And that's a really similar thing to NatRef 2022, where yeah, you
Sure.
get your latitude, longitude, and height, and that tells you, well, if I start at the center of the Earth and go out through the rotation axis and come out through the prime meridian at Greenwich and apply these numbers, this shows me where on Earth I am. So
Yeah.
yeah, I guess there's different ways of doing it.
That's awesome. We'll go to George, and then Steve had a question in the chat. You obviously wants to know when the GPS on benchmarks page is going to be updated, but we'll go with George first.
Okay, 41 years licensed, 56 years, I think, surveying, give or take. The numbers have gotten a heck of a lot bigger, but unfortunately, my brain hasn't. But good information. Good job, Jacob.
Yeah, I love it.
It helps me a lot. I can't even run a lot of the equipment today, but I still have to deal with the data.
Yeah, that's a great
Yeah,
point.
So thank you.
yeah. Thanks, George.
And Steve wants to know when all of his hard work is going to be updated.
I need to prod Galen again about that. It's come up in recent conversation. So
That's awesome.
yeah, you're right. We do owe that to you to have a wrap up come out to. And I guess I've been seeing each of these GPS and benchmarks campaigns as milestones. We're moving into time dependent reference frames. We can't close the door and say, well, we're done collecting data. Here's the new way of doing it. No, we need more frequent updates. But on that same token, I think we also have to come up with a really clear strategy about how can we most effectively take that data in for keeping these updates on track on a good routine. But I'll prod Galen about that again.
There you go. um, there's not been a lot of GPS and benchmarks lately. Are you still taking submittals at all, or what's the
Yeah, the
still
door's
going?
open.
Okay,
Yeah,
cool.
go ahead. Yeah, we're just not pushing it like we were
Yeah,
because we were really making that big push before we did the data pull for the reference epoch coordinate adjustment.
right.
But now that that's in the works right now, we're kind of in this in between phase. But keep collecting data because we don't want to have a big gap in the record.
Mhm.
At some point, we're going to have to go back and reprocess again and keep updating all of this.
Got it. And then doesn't get talked about a lot, but what about, Opus Share as well? People just kind of setting control points and then submitting them for Opus Share and that kind of stuff. How it just
So,
there's really not an importance behind it or campaign behind it. So I just
well,
conversation.
what Opus Share did is it opened up a way where we could take in a lot more information than what we had previously. And this gets into more of the science and modeling side that you see across the different areas of NOAA, where a lot of the other NOAA office is, if they're looking at ocean currents or something, yeah, they have their places where they operate their instruments, but in between there might be a way to get extra information from some lower quality that can come in and get downweighted for the modeling aspect of it. So it's when it comes to some of the scientific modeling, um, some of these people will take in everything that they can find, and then they'll clean out the lower quality stuff and end up using about 10% of what they originally had for making the model. So I I think with Opus Share, that was the big one of that was kind of the mindset of it, where yeah, you could go out and get a quick observation and send it in. And if it's on an existing mark, we can check it with other observations on that mark, and we can give it higher weight because okay, it's doing what we expect it to do. It's not way off, or we don't have some kind of a bust in the antenna height or something weird like that.
Sure.
But at that same time, if it's just okay, we got that one measurement, send it in, and if there's no redundancy or things like that, it may not help out as much. So that was where we're moving towards where this is all going to go through Opus projects and not through Opus Share so much as the future comes. So I do want to start pushing more Opus projects as opposed to Opus Share. Opus Share is still open if you want to send it in, but that's where that's kind of the difference in the data that you're getting, where something that goes through Opus projects goes through a lot more rigor. You have a lot more checks that go into it, so you know the quality a little bit better. Whereas Opus Share, it's here, we'll scrape it up, we'll use it, we'll average it out, but it's they both kind of serve different purposes. So
got it. Perfect. That was a great answer. Question in the chat about in their area, they don't have much GPS on benchmarks. Does that mean our vertical transformations to NAPGD are going to be less accurate?
That's and that's where the transformation tool is one thing where you get that mapping rate transformations. And so, yeah, I guess where that really comes into play is when you have an NAVD88 data set that you're trying to move over in an AppGE 2022. How good is that that model in that area? And I think overall, there's probably there's a chance that it won't be as accurate as an area with more dense GPS on benchmarks. I think it's still going to be good, and I think you can really see that in that plus minus that's in the model too, where you can see how much it changed from NAVD88 to NAPGE 2022, but you can also see, yeah, it changed 1.3 meters plus or minus, and maybe it'll be 5 centimeters if there's not a whole lot of GPS on benchmarks in the area, and maybe it's better than that if you do have it in the area. So I think that's one of those questions where it's going to take a quantitative mathematical answer to really get down to it. But I would expect areas with more data are probably going to have a better transformation to model.
Perfect. Any more questions?
Hey, Trent, can I ask a follow-up question?
Absolutely.
Sure.
Thanks. A great presentation. Fascinating. Yeah. So I'm with the municipality of Cincinnati. We're still on NGVD 29 still.
Okay.
Are we going to have the tools? Are you going to maintain the tools, or do we have a certain amount of time we have to catch up? Thank you.
So yeah, if you're on 29 right now, I'd recommend getting up to 88 as quickly as you can. So yeah, I'd say go out and resurvey if you can do that now, because the alternative is we're not going to publish a transformation between NAVD or NGVD 29 and NAPGD 2022. So if you're going to go through the transformation route, you'd have to go from 29 to 88, which has its own error that gets added in there. And then you'd have to go from 88 to NAPGD 2022, which has additional error. Second of all, NGVD 29, that datum's almost 100 years old. So it's been a long time since we did that adjustment. And the marks that are in use for it, if they have any sort of a stability issue, that's a long time to go to where additional error might build up. Access may not be as good as it once was. And I know you're not the only municipality in that boat. You're not the only
I was just going to say, yeah,
agency
yeah.
in that boat. But yeah, I would say if you can get moved on to 88, I think that's going to do you a lot more good.
Just even, I mean, I can't even imagine that. You know, there's tons of municipalities out west as well that are still on 29.
Yeah.
I think Phoenix and Tempe and some of these big metro areas are still on 29. It's like, you know, where's the fiscal impact when you're trying to deal with legislation changes that, you know, still writing, some of these states are still, even Nevada, we're still trying to write ours to get in legislation. But so, you know, there's a massive fiscal impact when it comes to all that. So,
right.
That'll be interesting. Interesting conversation. That's a whole nother show.
Yeah. Well, that's a lot of infrastructure that's tied to it too.
Yeah,
so
exactly. Interesting.
Yeah, right. It's not a quick answer. Let's put it that way.
Yes. No, of course. That's awesome. Any more questions?
I'm sorry. I'll try not to take too much time, but last question. This is so fascinating. So on the horizontal side, if I can say that, my understanding is that you're aligned with the ITRF, right? What about on the vertical, the geoid? Is there any alignment, any work with the international at the international level?
Actually, that's a really good question, or at least I think it's an interesting answer. So for developing NAPGD 2022, it's a series of, it's the geoid model, it's the surface gravity model, it's the deflection of the vertical model. That all comes from the same set of information. So we're actually developing it together with Mexico and Canada. We're using the same data set, and we're comparing our models to make sure that everything aligns, that everything is consistent. In addition to that, so what the datum point is for NAPGD 2022, so it's not sea level at a particular tide gauge or average sea level at several tide gauges. It closely approximates mean sea level from all around North America. So that was determined by satellite altimetry, as well as from tide gauge observations. So that value, it's a W0 value, which is in meters squared per second squared. It's geopotential. It's pure geopotential. Meters squared per second squared is potential energy per unit mass. So if you think about it that way, meters squared per second squared, if you divide it by acceleration for gravity, meters per second squared, you're left with meters. So that gives you a height value, and that's actually what we call dynamic heights. And that tells you purely how water is going to flow. Orthometric heights give you a really good idea of what that is going to look like, but dynamic heights are what truly show that. However, they're not a distance at all. It doesn't have anything to do with how far you go through anything. It's just differences in potential energy. And I actually have another talk about that. but yeah, so the W0 value that we're using was agreed upon by the U.S. and Canada, and it matches. And I know it spells it out in Blueprint Part 2. That there are several different bodies, different organizational bodies with interest in this number. And the International Association of Geodesy uses a number that works for worldwide use, so mean sea level all across the world. The value that we use is off by, it's about 2 meters squared per second squared, so which isn't really that much, but it's enough to make it where it's different, and why we picked what works for North America instead of what works worldwide. And there were, I forget if it was the IAU, the International Astronomical Union, that uses the same number. There was some other group that does from an international sense. But for heights, though, so with the geometric, we have the International Terrestrial Reference Frame, and that's been worked on for about 40 years now through different groups working together through International Association of Geodesy. More recently, there have been efforts to develop an IHRS, International Height Reference System. And one of the first things is select that number. And then some of the other things are come up with a global gravity data set that's consistent. And that actually takes a little bit more work. Processing GPS orbits and ground positions takes a lot of effort, takes a lot of time, but this is something that's consistent. A core is logging data every second. When we process every 30 seconds. A lot of that can be automated. On the height side, it's really not at that point yet. Where we do have satellite altimetry, which gives information about what the water surface over the ocean is doing. But that only gives you the longer wavelength aspect of it. Well, then we also have the GRACE satellites, where that gives a gravity model. But again, that's that longer wavelength. Now, with the height system, like what we're doing for our datum here in the US for NAPGD 2022, yeah, we're using GRACE, we're using altimetry, but we're also using our airborne gravity data set, where we flew at a low altitude over the entire country to get gravity differences. That gives us the medium wavelength. We also use a lot of ground gravity data where it's available, and that helps fill in those gaps and get a better model. Worldwide, we're still a long way off from having something at the airborne gravity level completed for the Earth. And the terrestrial gravity data, even if you grab all these different data sets from all over the world, they're going to be patchy, but they're also going to be really inconsistent. And they're going to be inconsistent with how they were collected, what the standards were, and the formats. So on the gravity side, on the height side, there's a lot more work to do before there's an international height reference system. I think some of the early groundwork is laid, but it's not ready the way that the terrestrial reference frame is.
That was like you said, a whole nother presentation just on that.
Yeah.
That is awesome. There's the Cliff Note version of that. That's cool. Yeah. Great stuff. Anybody else? It's always fascinating. I know we've been talking about it already for a long time, but obviously we still got a few more years to go, but we will have the challenges. Yeah, I was going to say it's coming up quick, but then we'll have a whole nother set of challenges, but nothing this week. Good stuff. I always appreciate your time. So that was great as always, but if nobody's got anything else, then we'll get you back to dinner time for you, or actually it's 8:30 for you. So
yeah, it's almost bedtime for me.
Yeah, that's right. It's almost bedtime for you. Dinner time for me. So
yeah.
Awesome.
Right. Thanks, Trent.
Awesome. Everybody have a great week. Bye guys. Yep.